Hello everybody and welcome back. In the last couple of episodes I did some brainstorming on different approaches to forecast the track of hurricanes and different ways of looking at the data. Then I did some experimenting around. I tried using a pix-to-pix GAN implementation and a simple convolutional neural network to forecast the future positions of these hurricanes using two different data structures. And while both approaches showed a great deal of promise, the accuracy of each during this initial round was quite low, and the systems took a very long time to train. This led me to consider the idea of using autoencoders, a self-supervised learning algorithm, as a way of sort of pre-training a large portion of our system using unlabeled samples, which could help expedite further experiments down the road around the overall system architecture. Well, I've spent the better part of the past couple weeks experimenting around with this concept, and I've been able to successfully build and train a 6-channel, 3-dimensional autoencoder to work with our spatial data set. As far as I can tell, this is the first of its kind as well, which is pretty cool. And beyond that, it fills an essential role in the overall system design that opens up several possibilities that were originally closed to us. Now, I can't reinforce this point enough. We need to remember that the engineering design process is iterative. The first time we went through the conceptualization and selection stages, we didn't really have much by way of a fully formed system concept or concepts. We just had pieces that each addressed a small part of the overall problem. However, after running through some experiments over the last few days, a couple weeks really, a few potential initial design concepts are starting to coalesce. So, in this episode, I'm going to first spend some time going over my new autoencoder setup. I'll show you how I set that up, what the results look like, and lay out a few competing ideas for how to improve it moving forward. Then I'll select my favorite and lay out my first real design for a complete system, or my preliminary design. And then in the final episodes, we'll circle back again as many times as needed until we have a workable final design. Now, as a quick side note, the design build portions of this process lend themselves nicely to the Agile Scrum framework. This is a process for project management that pretty much every software development company out there uses. Agile Scrum is not an alternative to the engineering design process. They both serve very different purposes. The engineering design process is a set of steps designed to create something new. As its name implies, it's a process for designing. Agile Scrum is a project management process that helps prioritize and schedule chunks of work in the form of user stories that are typically intended to add incremental improvements to an already existing design. If you wanted, you could even use it to manage the design process, but ultimately you'd still follow the same steps outlined by that separate design process. It's a workflow management system as opposed to one intended to spark creative new ideas. So again, these concepts are separate, but they can work together to great effect, particularly with a large team. Now I'm not going to use it here since it's just me working on this thing, but if you want to learn more about it, I'll add a link to some further reading in the video description. Okay, so let's get into my autoencoder implementation. So this essentially all works in 4 steps. First, we need to go and extract the information that we want from our netcdf files that we downloaded from NOAA. And these netcdf files are all located in a single directory. Eventually, I'm gonna go and generalize this all a little bit more and kind of stick it together into a single coherent package that we can use to train a given set of netcdf files. I think that would be an interesting thing to have in general for solving geospatial related problems using machine learning. So I'm going to split this off into its own repository and do all that. But for now, just kind of bear with me. This is a kind of a quick and dirty way of doing all of it. So what we do here, we have this load year function. This load year for a given year will open up the 6 files associated with that year. So for each year, we have a file for the air temperature, one for the height, the pressure height data, one for this omega variable, relative humidity, the U component of the wind speed, and the V component of the wind speed. So load year will open 6 files and use the data set object that we're able to create through the netcdf package to extract all that information, put it into NumPy form, and then use NumPy's stack function to glue it all together into a single big array. That array is then pickled here using Python's pickle package. Here we build a data generator object. So this is a class that we will instantiate later that will essentially contain all the functions that we need in order to create samples for our Keras model to train with. Now the samples this will generate will all be from 1979 through the end of 2012, because 2013 through the end of 2017 is what the National Hurricane Center uses for its verification of the performance of these models. So we want to set that aside and use it as our test set. So data generator is generally, if you follow the documentation available through Keras, data generator will only is usually done using just a simple function that returns, your next sample of data. Here we're doing something a little bit more complicated. Now I follow the general approach that Stanford published on their blog entitled, How to Generate Data on the Fly for Keras, How to Generate Data on the Fly. And this was very useful because it used this alternative sort of method that goes a little deeper. It creates this data generator object that inherits from keras.utils.sequence. And this thing was a lot more flexible. And what I needed to do though with this approach was essentially fill in from the back this get item method. So get item is what gets called by the fit generator function within Keras, like when we're running that on our model. This is what spits out this next sample for training. Now with an autoencoder, remember this is a self-supervised algorithm. We're essentially just using the input as the output. So with an autoencoder, we want to take the raw input file, encode it, and then decode it back into something that looks like that raw input file. The error is the difference between the raw input and the output. So here what we're doing is we're just essentially going to send, this is X, this is what we're inputting, our samples, but then we just send them again for Y. This isn't the most efficient way to do this because we're essentially sending this data twice. But it works and it gets us some results. So, it's a little bit of a workaround. There's definitely got to be a more elegant way of doing this than just sending the data twice, for each sample. But regardless, it works. Now, one nuance here is generally when you use a data generator, you would use yield to return the samples instead of return. However, I was encountering bugs when I did that. For whatever reason, in this case, using yield worked better. I should say it worked without errors. Now, it may have something to do with a bug within keras.utils.sequence. I don't know, but that's just something to kind of be aware of. And next, I should just point out that this thing does more than just generate samples. There's a lot of logic behind the scenes here. I mean, even just the process of generating those samples, I use a couple different methods to pick those like random samples from our entire set of data that we have available within each epoch. But it does it so it only goes over each sample once. So as they get pulled out, there's a weight that gets recalculated based on the number of times that sample has been used. If it's been used the maximum number of times of any of the past samples, then it gets a 0 weight essentially. And so that is a way of ensuring that we only pass over each data point once. So that's what that's doing. But there are a couple nuances here I also need to explain. First, there's only 1 year by default in each epoch that this will go over before the on epoch end gets called. So when we go and run this thing, we need to be aware of that. An epoch with this data generator is not equal to one full pass over the entire data set, which was 30 something years, 38, 39 years. It's only 1 year, a small fraction of our overall data set. That's not technically correct. You know, we generally want one epoch to basically mean one pass over our full data set. But in this case, I couldn't find an easy way to make that work. We had to load these huge multi-gigabyte files, which takes several seconds to do. And so for me to, with each sample that gets generated, have to open up a set of files, or just iterate through 1 year at a time, or a randomized set of years, but stick to 1 year at a time as I went through the full set. It would have taken way too long. A single epoch would have taken probably an hour or two for this thing to just go through. So instead, what I'm going to do is have one epoch within here just equate to 1 year of time. And what we'll do is we'll set it accordingly with the number of epochs that go into the full training, so that instead of just doing 4 or 5 or 10 epochs, we'll do a few hundred epochs. So we're sure to pass over each of those 30 whatever years at least a handful of times. So that's just one thing to be aware of. A little kind of quirky thing with how I had to implement this, but aside from that, it's all pretty straightforward. One other thing I think I should probably spend a little time explaining. Well, I guess there are two other things. First is normalization. Okay, so when you generally train a machine learning algorithm, you want each column to be in the same sort of numerical scale. Like we have here, like each column within our X, if we were dealing with a standard, two-dimensional X and maybe either a vector or a two-dimensional array for Y, each row represents a sample in that case, and each column is a feature. In our case, we have 3D data grids, so it's a little bit more complicated, and actually really 4D data grids, because we have multiple variables at each data point. But anyway, we want to generally normalize each of those inputs so that they're on the same time scale. So when we train our neural network, it doesn't have a bias towards the ones that are the biggest. In our case, we have pressure, and temperature, and relative humidity. Relative humidity is going to be a very small number less than 1, I think. Those are fractional numbers. Our wind speeds could be a couple dozen. We could see 30 knot winds, or even higher. Actually, we're looking at hurricanes, so we could see 100 knot winds. But temperature, that's Kelvin, so we're going to see that is going to be in the hundreds. Pressure is going to be a pretty big number, but the pressure, we're actually looking at the heights. That's the way we see pressure here. And those height numbers are going to be huge. They're going to be thousands. So we have right off the bat, this thing's going to be more biased towards certain variables. Things that are smaller numbers like relative humidity aren't going to be factored in as well. And so we have to normalize our data. Now, this is a little bit more complicated than what we would normally do. Normally we would just use scikit-learn's either standard scalar or minmax scalar functions to do that. But because we have 3D data grids, we need to be a little bit more methodical with it. So in this case, what we do is we simply iterate through. We pull a sampling of years. In this case, I pull a sample of 5 years. For each variable and pressure level pair, I calculate the mean, the standard deviation, the minimum, and the maximum. So for each pressure level and each variable, I calculate those values, and then I store those into a matrix, a pretty small matrix relative to most of these data grids, but still more complicated than what we would normally be looking at. In the future then, next time I go through and I create a data generator object, what I'll do is load those values and then use those to normalize everything else. So again, the reason I'm looking at each of the variables independently is because obviously those are different ranges, but I also, the pressure levels, now think about it, like as you go high up a mountain, you start encountering snow because it gets colder. Pressure goes down, temperature goes down as you go higher and higher up. So if we were using the same scale for sea level, things would look very different at that pressure layer than they do at the one corresponding to, say, around 10,000 feet up. So I just want to make sure that those scales all get done correctly, and that we're not having certain pressure layers that have very high values versus others that have very low values in general. So that's why I go through each pressure level and do it this way. Anyway, when we get into creating a new instantiating a new object of this class, we'll go and load those values again and then normalize each year's data as we load it using either the min-max method or the standard scalar method. Now min-max, what that does is it puts every value in the range of 0 to 1. Standard scalar sets the mean to 0 with a standard deviation of 1. So standard scalar maintains more information about outliers than min-max does, but that also makes it like a little bit more risky because if you have outliers, say your data scrubbing wasn't quite comprehensive enough and some really strange values sneak through, you can really throw a training session out of whack by throwing like very large or very small values at it during training. Min-max will use clipping to make sure that doesn't happen. You can do the same thing with the standard scalar approach. You can clip it so that it only has values within plus or minus, say, 2 or 3 standard deviations of the mean, but that's just not the default way of doing it. So I default to using min-max here, and if you want to use the standard scalar approach, all you do is you set normalization mode to anything other than min-max, but that's that. So the other thing I want to point out is this expanddims method. So expanddims is just essentially, in order to explain why I have to do this, I think I have to move on to the next step. So once we've got our data generator in place, now it's time to create our model. So we pull it, we call it here with our different parameters, and then we have all our different layers here. Now, if you follow the tutorials on Karis's blog on autoencoders, you'll see that this looks a lot like one of those examples. I just swapped out the 2D convolutional layers for 3D. I've added a little bit more to it. Have 2 convolutional and max pooling steps, both on the input as well as the output, I should say, both on the encoding as well as the decoding piece of this. But whereas none of those examples really show how to save the decoder on a multi-layer model like this, I had to go and do a little bit more digging to figure all this piece of it out. But essentially what I'm doing is creating 3 models here. The overall autoencoder, which is everything, the encoder, which is just like the first half of it, and then the decoder, which is the second half of it. Now the encoded layer here is not actually flat. Later on, I think I do something, I have to dig up where, but I will essentially flatten that and store it and work with it as if it were flat. But why I had to do that padding approach, if we have combinations of convolutional and max pooling layers, we're going to end up outputting a different size each time we go through these steps. So the input is going to have however many let me think. I think it was, yeah, 73 latitudes on 144 longitudes. It's 17 different pressure layers. You know, but as we go through here, we have, I think it may be half as many, or like half the dimensions. But like as we go down to encoding and then back up to decoding, if the dimensions aren't divisible by 4, you know, because we're doing this twice and like dividing the output, I think twice, or by 2 twice, when we reconstruct it and we go and upsample, you know, as we go and create our encoded output, or decoded output, I should say, sorry, we're going to end up having a mismatch size. So these dimensions get off when you reconstruct it. So the workaround that I found was to ensure that all of these were divisible by 4. So I had to round up to the nearest number divisible by 4 on all axes. Really, that just counted these two. So the way that I did that, just going back to the data generator right here, is this expanddims method. That goes and creates a temporary array using NumPy zeros function. So I create an array of zeros of the given dimensionality that I want, and then I copy in the data, you know, into there wherever we have it. So that's all that this thing's doing. It's padding everything with zeros after it's been normalized. So that allows us to have an input that has the same dimensionality as our output. It's just got like sort of this border around the outside. But you know, the alternative to doing it that way is to, instead of rounding up, we would round down and clip out a bunch of our, or I should say crop out a bunch of our data, which is not ideal because we would lose some pressure levels and we would lose some latitudes and longitudes in the set. So, you know, that's why I did it this way. It did seem to work. I'm skipping ahead a little bit, but it did seem to work. But one of the things I may try moving forward is cropping and see if it works better that way. Now, once that's done, we need to encode our data. So this piece of it goes back through and it loads each of those pickles that we previously created and runs it through our trained models. So back in the autoencoder step, the last thing that happened here was I saved our trained models. Oh, one other little nuance I want to point out. I did not use multiprocessing. I only have it set for 1 worker here. You can increase the speed to some degree by increasing those. Just be aware if you do this in Windows, that won't work. There's a bug with using fit generator with multiple workers in Windows. It just won't work. But I don't even know if that would necessarily even help, because ultimately this whole thing was limited in a big way by the time it took to load from the hard drive. I think would have seen an increase for a few, like maybe if I went up to 3 workers. But the time it took to load an epoch was definitely a bit longer than the amount of time it took to train an epoch. So, you know, maybe if you get up to 2 or 3 workers, you'll probably find a point of diminishing returns around there, I would wager. But still, you can speed things up by doing that within Linux. Now, once that's all trained and saved, we load those models again, and then we go and load each of those pickle files that we previously saved. We reformat them in the same way, you know, normalizing them as well, the same way we did with our data generator before, only now we have to do it manually because we're loading those pickles, you know, one at a time. So I'm just pulling that same code and doing it over again here. Once that's all loaded, we use our trained models, should be predict function somewhere here. Yeah, right here. To encode everything. Once we have our encoded values, we reshape them. Yeah, this is what I was referring to here, because it wasn't a flat output. We had essentially a convolutional layers output. So it was you know, I think a 3D array. So we needed to flatten this And once that's done, we add the dates in, because we know that one of the axes of each of these files was a date time, like every 6 hours throughout the year. So we go and calculate that, and make that the data frames index, and then just kind of stick it all together. So in the end, we have a huge data frame that literally includes every time step of every year just encoded. And this is something that we're able to fit into memory, which is amazing. So we'll be able to just load all of our historic data now, which before was hundreds of gigabytes. We can load it all into a couple dozen gigabytes of memory. Okay, now the last step here is to visualize the data. I put together a new script for this. So if we go to visualize samples, this looks a lot like encode data. It's because I built it off of this, but it's essentially just has a little loop at the end. It's a little more simplified. That goes and loads the saved pickled encoded data, and then just uses that to generate some visual samples from the test set. So one thing that's important to note that I think I forgot to mention earlier was that when we generated the samples for training, I limited the range to 1979 to 2013. Now this is because 2013 through the end of 2017 are considered the test set for the NHC evaluation, or verification, I should say, of various systems performance. So we want to leave those alone, if at all possible, for the purposes of benchmarking later. So I left those out intentionally from the test set. Now here, what I'm going to do is take an early sample from 2013. So this is not something that we trained on, but I want to visualize, what do the auto-encoded versions of the raw input data look like. So this basically just does that. It's pretty straightforward. And so I'm going to jump over to the results here. Okay, so you can see here a side-by-side comparison of the input data to the auto-encoded version of that. This is from the test set, 2013, January 1st, 6 p.m. Greenwich Mean Time. This is the second pressure layer from that time step. And you can see that, that it's pretty close. I mean, the encoded version of that data does capture quite a bit of the detail. Now again, keep in mind this is the test set, so this was not used in training, this example here. And I am very impressed by how much of the detail is captured, especially when you consider the compression that we're working with. So this is a zoomed in version of the temperature, and you can see on the left is the raw NumPy data here. So this is just that one variable at that one pressure layer at that one time step. And you can see there's quite a bit of detail, like you can see a lot of the swirling patterns that we would expect to see in the atmosphere. On the right, the auto-encoder output version of that is definitely not as detailed, but you can see the general gist of everything, like the dark spots are generally in the same spot. You can see some of the swirling patterns, but the resolution certainly could be improved. With that said, the original NumPy data was 294 gigabytes. The auto-encoded output for that full set is 13 gigabytes. So it's about 4% the size, or over a 20-to-1 compression ratio that we're getting on this. And that allows us to load the full training set into memory moving forward. So we can take all this data and then merge it together with track history or some other inputs that we want to bring in. We could do something similar with wave watch data and bring in ocean currents or things along those lines. And we have data sets that are small enough to load into memory. I do think we can also improve this. 13 gigabytes, my system has 64 gigabytes of RAM, and I would like to see something with a little bit more resolution. So I'm gonna tinker around with the autoencoder and see if I can make it work a little bit better and capture a little bit more detail over the coming weeks. And I expect I can get something that, to at least the human eye, would be indiscernible here. So in the meantime, this autoencoder concept gives us several obvious options for an overall system design. The output of an autoencoder is flat and can feed into any number of machine learning algorithms, at least those that are capable of generating multiple outputs, such as neural networks and random forests. But regardless of which algorithm we use, or which algorithm this feeds into in the end, there are a couple key design questions we need to answer. First, how should we structure our input data to our autoencoder? Should we continue using our three-dimensional multi-channel data structure? Should we split it up into several two-dimensional single-channel layers that get brought back together? Or should we do something in between? Personally, I'm inclined to at least keep the channels together. We know that that there are certain physical relationships between these atmospheric variables. The ideal gas law tells us that pressure and temperature are related. So we would expect to see features involving these variables align spatially. And wind is just air moving from areas of high pressure to areas of low pressure. So we would expect to see wind related to pressure and therefore temperature as well. So splitting these up and looking at them independently could cause all these variables, these channels, to become disjointed. I don't really want to do that. I don't want to split these up. And same is true for the layers, the pressure layers. We would expect to see some alignment, at least from one layer to the ones adjacent to it, above and below. Now, overall, I do think that the 3D approach is pretty elegant, and I think with some extra effort here, we should be able to improve its performance pretty significantly. Now, next, we need to consider how to convey the location data to our neural network. In my previous convolutional neural network implementation, I added a separate color channel that contained a flat image with a single dot located at the eye of the storm. We can do something like that here, adding a dot to the latitude-longitude coordinate at each pressure layer. But what if there are two storms active at a given time? Do we make two copies of the input set with a single storm tracked on each, or do we put multiple dots in there? Or do we just leave the location data out completely and instead bring it in via a second branch of our overall system architecture, like they did in that fused network paper I keep referring to? Or do we take another idea from that fused network approach and center our maps on the storm instead, but still keep the full globe included instead of just a limited window around the storm? We could even take this idea a little further and have our system output be a relative change in position. I did a little bit of experimenting here, and it's nudging me towards an answer. I took my trained autoencoder and used the resulting encoded states as inputs, along with the current and last known latitude and longitude coordinates of the storm, to train both a random forest as well as a simple, fully connected neural network. The resulting system performed horrendously, worse than anything else I've tried. Now, this fact, along with the much better results that the other machine learning approaches I've read about during the research phase, have me thinking that I should lead my efforts, or push my efforts more in the direction of centering the view around the storm. Further, if I make my output into a position relative to the current center, I think that will help constrain the solution space a bit and let this thing converge a little quicker. And implementing that should be pretty easy to do thanks to NumPy's roll function. That's what I'm working on right now. Once that's done, my plan is to feed several sequential encoded samples with their corresponding track location to an LSTM neural network. LSTM stands for Long Short-Term Memory Neural Networks. These are essentially neural networks designed to work with sequential time series data. So here it is, my preliminary design. We'll take a revised autoencoder centered on the storm, concatenate the encoded output together with the storm's current track data, or at least its current position, then stack that on top of a few past time steps to form our input for our LSTM. Our LSTM will output a relative position from the current center of the storm. In our next episode, we can check out how well this all performs. Now, until then, Moonshot out.